Okay, so this chapter, kind of unlike other chapters, started off with the technologies, rather than the science. But if we look now, we're on 8.3, and what we're looking at now are I guess we skipped this one last little figure in 8.2. This is showing the oscillating water column. So I guess what we're not really, somewhere down in here is the actual, the water sort of coming up under here. This is just sort of over spray, if you will, but inside this guy is the actual technology. And back behind it, of course, is that turbine we talked about. Okay, so principles of wave technology, 8.3. I'm just going to read through the three main points that the authors mentioned. It says, initially, air flowing over the sea exerts a tangential stress on the water. What does that mean? Well, here's the surface of the water. Here comes the wind. When they say tangential stress is kind of the advanced term for pressure. And I guess since I'm thinking about it, we're talking about it, let me just give you a quick little overview of what stress actually is in a mechanical sense. So if we just build a little block of matter here, this could be a chunk of air, could be a chunk of water, could be a chunk of some solid device. You probably know that force, so I'm just going to draw a generic force vector. Force is a vector. You can break it down into an x component, so f sub x, a y component, f sub y, and a z component. These are, in each one of these guys, it's hard to draw three-dimensionally on a two-dimensional plate, but each one of these axes is mutually perpendicular. This guy, the F, is, it's some combination thereof. So just again, a little hand puppet. Here's a surface. My finger is imparting a force on my hand, just like your foot would impart a force on the floor, or your car tire would impart a force on the road. You have a normal component, which is perpendicular, but you also have two shear components. That's what the authors refer to as tangential. So there are three fundamental components to force. It's a vector. It's in three space. That's where we live, and there it is. Now, if we have, instead of just a surface, so I'll just kind of, here's the surface we were talking about, right? So the force is acting right on that one little point. Instead of a surface, now you have a chunk of matter, air, water, wood, what have you. It gets a little more complicated. So you can actually have a force acting here. This is going to be F. I'm going to call it Z because it's in the Z direction. And it's also acting on the Z face, the top surface. I could also have another force acting over here. It's a force acting in the X direction on the X face. You can have another one over here, a force acting in the Y direction on the Y face. Okay, I just told you force is a vector, so it's got three components. So you can also have this guy, a force acting in the X direction on the Z surface. You can have a force acting in this direction. So that is a force in the Y direction on the Z surface. You can have another one over here, which is a force acting in the X direction on the Y surface. You can have one here, a force acting on, in the Z direction on the Y surface. keep going. You've got here a force acting in the, well, let's draw it the other direction. A force acting in the y direction on the x surface, and then finally you can have a force acting in the z direction on the x surface. We now have 9 forces to keep track of. We also have this area, which is the z area. We have the x area, and we have the y area. Now, if you divide force by area, you get pressure. So we all know that atmospheric pressure, 14.7 psi, pounds per square inch, force per unit area, 101 kilopascals, newtons per square meter. The engineering or scientific term for this is stress. And stress equals force over area. So I just showed you 9 separate forces. So there are also 9 separate stresses, and I'll just write them out. Well, let me write force first because it's kind of simple. Force, and I'll write it with one line underneath it, is a vector, and it's written like this. Fx, Fy, Fz. So you can kind of think of this back, to your algebra. If you've solved 2 equations, 2 unknowns, or 3 equations, 3 unknowns, that's kind of how you start writing your algebraic equations. That makes sense. Stress, sigma. That's the Greek, the lowercase s in the Greek language, sigma. Sometimes you'll see it with 2 lines under it for a different type of number. Well, just to complete the analogy. Pressure, we're not going to put any lines under that because pressure is what is known as a scalar. It doesn't have a direction. When you say, what's the atmospheric pressure? Well, it's, 1 atmosphere. It's number, 15 psi. What direction? Well, what do you mean? There's no direction to pressure because it acts the same in every direction. Well, stress, as we see now, has directions to it. And it's got 9 directions, but we only have three spatial directions. There's more directions of stress than there are directions in space. So it's actually called a tensor. Tensor, if memory serves me correctly, was the name that Albert Einstein came up with to describe it because he was talking about space-time. It's also used in solid mechanics. It's how the Eiffel Tower was built. Before scientists and engineers understood how stress worked, you couldn't build something that big. I mean, we built cathedrals and things like that, but really with very limited mathematics. So stress ends up looking like this, sigma xx. So that's basically this thing right here, sigma xx. So that's the stress in the x direction. Here's sigma xy, and so just look for wherever the xy is, or yx, same thing. They're really the same thing, because whatever stress is acting on the x surface in the y direction, you can also think of as acting on the y surface in the x direction, and I'll show you what I mean by that with my hands. So this little sheet of paper could be like a top view on that block that I just drew. So if I'm pushing in this direction, you can see that these shear stresses that I'm imparting are keeping this little block from rotating. So I've got friction going here, I've got friction going there, friction going here, and friction. They're balancing each other, so that the sum of those forces and stresses keep the thing from moving. And I promise I'll get back to the waves here in a second, but this is sort of putting in context what the authors were meaning. So you just kind of keep writing the thing out. I said there were 9 of these total, so sigma xy, or sorry, that's sigma xz. Here's sigma yx, here's sigma yy, here's sigma yz, here's sigma z, x, sigma zy, and finally sigma zz. So you've got 9 stress components. In solid mechanics, where things don't move, civil engineering, etc., these equal each other. Like I just showed with my hands. The shear stress, this arrow right here equals this arrow right here. They're equal and opposite. Same thing here. These two guys equal each other, and so do these. Equal each other. So, as it turns out, there are 6 independent components. These 3. This is why my notes never make sense after. These 3 are the normal, and these 3 are the shear. So, I am going to go right back to where I was reading in the book, page 369, 8.3, paragraph 1. Initially, air flowing over the sea exerts a tangential stress. What is that? Well, it's one of these 2 jobs right here. Because this is the sea's surface right there. I would draw in blue if I felt like it, but this is the surface of the ocean right there. I just drew water below, air above, and sigma xz and sigma yz are the shear stresses or the tangential stresses making the waves. Make sense? So long way around it, but that's what's going on right at that interface between the air and the water. Okay. Next thing that happens, turbulent airflow close to the water surface creates rapidly varying shear stresses. Now we know exactly what that means. And pressure fluctuations. What's pressure again? Well, that's more or less pressure we can think of at the surface is just this one. Pressure. Pushing down or sucking up, basically. That's what's going on there. Further wave development occurs. Finally, when waves have reached a certain size, the wind can exert a stronger force on the upwind face of the wave, causing additional wave growth. Okay. So this stuff, can become very complicated mathematically in a hurry, and let's just take a little look here, since the authors go into it. Kind of like this stuff. Okay, yeah, this is good. That very first image we looked at, I mentioned watts per meter, and what I'm about to show you is it's an example of dimensional analysis or units analysis, and it's going to be something that you're going to want to do in just about any little engineering technology problem you ever solve. You're going to make sure, like, oh, is this an energy equation? Is this a force equation? Is it a power equation? Because you can't have watts on one side and joules on the other unless you've got time somewhere in between, right? So that's what we're looking at right here. So we're looking at box 8.1. And what we've got is power equals density. So this is a P for power. That's a rho for density. Then we've got gravity squared. Then we've got H squared. And then we've got T, which is the period. And if you look back, you can see that the period is 1 over the frequency, or the frequency is 1 over the period, however you want to think about it. So T is going to have has dimensions of time or seconds. And then finally down here, we've got 32 pi. Okay. and the authors don't derive this. I don't, and off the top of my head, I don't know exactly where the 32 comes from. It could come from an integration. If you look at this, guy, it's kind of a funny combination. I look at this thing, and I think potential energy. Think back to your MGH, equals MGH. I look at this thing and I think kinetic. And so in some ways, it's a little bit of a combination of both. But let's go ahead and do the dimensional analysis and see if we can actually get the proper units. So rho is mass per length cubed. Gravity is length per time squared, so that becomes length squared over time to the fourth. Yeah, I hope this works out. Yeah, maybe. Okay, let's see. H squared, so that's height. Yep, height, and that's length squared. And then finally, time. So let's do a little simplification. And let's see, what do we have here? GH, length squared, length squared. Density, oh, yeah, nice, okay, cool. We got mass, we've got length to the first power, right? Because it was length to the fourth divided by length, and then over time cubed. You're like, oh gosh, that's kind of a mess. I've never seen anything like that before. Well, that equals mass times length squared over time cubed times 1 over length. Well, this hopefully you recognize as power, because if you remember, energy is mass times length squared over time squared. Divide energy by time to get power, and boom, right there it is. What's left over? Well, it's power per unit length. It's like I said, from the very beginning. So you look at this thing at first, like, what the? And this is actually, let's see, maybe we just write it like this. It's not actually power. It's and you can use whatever symbol you like. I wish the authors had chosen something, but I'll just call it P prime, or power per unit length, because that's what it is. So again, just to tie all that together, if we sort of look back at this guy, our very first item. So one would think that the wider you make this, the more power you're going to get, but you would also have you could think of as a specific power. How much power is there in this 10 meters? Well, divided by 10, how much power is in that little 1 meter there? That's your power per unit length. Add up all the meters, and that's how many watts the thing has. Right? So similar to what we've been doing with the wind turbine, you can do the same thing for geothermal. Make the system bigger and more power comes in. Okay. And this is what I really appreciate about the engineering discipline. I mean, it just allows you to take what seems like kind of a new novel thing and just break it back down into things that you already know. So it gets tied back together. Okay. So that was box 8.1. Look at these guys now. Okay, so one thing the authors mentioned, to build one of these tap chans or oscillating water columns, what you'd really like to have is sort of a consistent, predictable flow of energy, and that's going to drive your economics, your return on investment. So the waves themselves can be quantified, measured on these metrics. Little waves with the little wind, bigger waves with the big wind, and if it's really honking for a long time, here come your big waves. If you've ever been to Flathead Lake, you've probably seen that. You're over there on the western shore, little tiny waves. You get to the eastern shore, and they're just blamming away because they've had, I don't know how wide the thing is, a mile or two to build up and smack on the shore over there. There's a project, Energy Tech, Tapchan, Flathead Lake, power the rest, Finley Point, whatever. Let's see if there's something there. Might be fun. But obviously the waves themselves have a height. In electronics, you're going to call that an amplitude. So this is a mechanical wave instead of an electrical wave. It's got a wavelength. That's sort of the opposite of the frequency, if you will, and then the speed. So there's, besides the water depth, how's the water depth going to affect this thing? What's going to happen when the water gets more shallow? Yeah, well, it's similar. It's similar to that Tapchan. It's almost like a built-in Tapchan. As the water gets shallower, there's nowhere for it to go but up, and you get those big curlers. So the water depth itself, as that decreases, your water's flowing uphill. There's nowhere for it to go, and you get the curlers. The wind also has an effect on that. Okay, so there's just three little waves, but in reality, this is kind of what's going on out in nature. Same deal with wind farms, not exactly predictable. They're up, down, all over the place for the surface level. And here's another one. I don't know if this is, well, it says this is actual data. It says 2 further wave records shown for the same location, different days. So bigger wind, bigger waves coming through on the green day, and then you can go along and plot these. So you can also think of this as just like a radio station, right? So here's high frequency, low amplitude. Here's low frequency, high amplitude. Little AM, FM on your wave dial. And then, once you have taken enough historical data, you can put together a chart that looks like this. Once you've got this chart, then you can take it and say, this is the type of wave technology we're going to need to build based on the what's coming in here. Okay, so we're calling this a scatter diagram of significant wave height. So that's H sub S, so for significant wave height. And each one of these is in meters, so this is a wave of 1 meter tall, 2 meters, 3, 4, 5, 6, on up to 14. And each one of these, each one of these lines that we see here are constant power. So if you've got, so let's look at this for a second. So if you've got a relatively high wave, and it's coming in frequently, every 7 seconds, you're going to have relatively high power. You could have the same high wave, but if you come over here and it's not coming in as frequently, then the power is lower. That's why these blue curves sort of swerve down and to the left. So they're accounting for both how high it is and how frequently it's coming in. So it could be that this little orange line has got more power because it's coming in more frequently. Just think of just think of something hitting a surface lightly and frequently. Okay, I'm doing work versus one big punch that's the same amount of work got done. It just happened over smaller increments versus one big smack. So that's where these lines are coming from on the scattergram. Okay, so then it's our job to come in here and look for the sort of the sweet spot. Like, gosh, this is great. This is a very, very powerful wave. We're looking at power densities of, gosh, a kilowatt per meter. Kind of different. But pretty good. I mean, if you think, so to run a house, you need 1 kilowatt. If you could run your house off of 1 meter of beachfront property, not too bad. Like, how much shoreline do I need to buy? I'll just take this meter, run your house. Yeah. But if you're like, oh well, I've only got a power density of 200, well, I need 5 meters then, please, to run my house. Okay.
I don't know, I might need 8.
You might need 8. Yeah. You run. What do you got? Electric heat or something?
Oh, I got teenagers.
Oh, teenagers, yours.
I don't think they even know what a light switch is.
Yeah, I'm going to go to Missoula Federal. Actually, I've already been to Missoula Federal Credit Union, and I'm going to go to the Five Valleys High Performance Building Committee, which I'm a member. It's just an informal group of folks trying to get her done. And what I'd love to have right now on my phone is the buttons to turn off the lights in my house. Wouldn't it be nice? And they're out there. I mean, it's not new technology, but it hasn't really reached the mainstream, and it's still coming to Montana. But that's what you need. Just turn, or even laying in bed at night. Oh my gosh, turn the lights off. So it's coming. Needs to happen. Okay, so back to this figure though. The numbers on the graph denote the average number of occurrences of each combination of H sub S and T sub E in each set of 1,000 8.6 hour-long measurements made over 1 year. So somebody actually, this is real data. Someone sat there with their height meter and period meter and measured for a full year. And you can see that there was one fine evening where a 1,600 watt per meter wave came in. I'm a little surprised it's so sparse down here. They might have just cut out a lot of this other stuff or just looked, kind of been selectively looking in here. But, there's a 42 in there, there's a 39, so this is kind of your sweet spot. We're looking at, 20s and 50s of kilowatts per meter. Yeah, okay. Yeah, so that's actually kilowatts per meter. That's even bigger than I thought, 1,000 times bigger. All right, so that's just at one particular location. Yeah, and these numbers are a lot bigger than you think. So you look at the North America, 33 kilowatts per meter. That's actually pretty dang good. It means that in 1 meter of North American shoreline, you can run 33 homes. Not too shabby. Seeing 97 down there at the tip of South America. Some good juice. Yep. Alaska's cranking. India not doing so hot with 8.3. A little more protected there. Same thing up around the Scandinavia with 2s and 3s, but they're not having the advantage of the open sea sort of crashing in there. All right, let's just do a little bit more here. Look at the physics of what's going on beneath the surface, and then we'll take it from there. Okay, now I did spend a little bit of time there developing the stress tensor for you. You can also see that velocity itself is also a vector, right? So at the surface of the water, you can have a velocity that's basically blowing the wind in this direction and making waves that are perpendicular to it. You can also have wind that is blowing in this direction and making waves perpendicular to it. Those two velocity vectors may or may not be parallel. In fact, they're not. They might not be perpendicular. In fact, there's some combination thereof, but you get enough of them together, and then you kind of end up with this interference pattern in general. So that's just sort of the combination of all of the various prevailing winds coming in, and then you come up with this sort of radial or directional rose, they call it. Same exact thing is going to happen for looking at a wind farm. So when Brian Kearns goes out and scouts for a wind farm, something like this comes back, and basically it says, point your technology over here, or point it somewhere between these three vectors so that you're harvesting the maximum amount of energy. Because if your tapered channel or your oscillating column is not pointing in the right direction, it doesn't work. It's like having your wind turbine pointing sideways instead of straight ahead. Okay. And an anemometer can do that. The anemometer spins with the wind and tells you how long it's been blowing in a certain direction and how hard. Okay, now, so another result of these shear stresses is that the water at the top is moving faster than the water at the bottom. So when that happens, and it's kind of difficult to visualize sometimes, but you actually get circulation. Now, some of this water does travel in towards the surface, but water, like any other substance, is going to take the path of least resistance, and most of it just stays put. It just sort of, does a little roll, comes back, and it's just sort of sitting there, making these little turbulent eddies on the surface. You go further and further down, and it's less and less prominent. You might say, well, gosh, how this, if this circle is going here, shouldn't this one be going here? Well, it is. It's just kind of a simplification showing that in general, whatever momentum on the surface is transferred, at some point, there's really no effect. Anybody sitting on the seabed is not going to know what the waves are doing overhead. And that's basically what these little circles are doing. So, diminishing power from the waves as you get further beneath the surface. Okay. Table 8.1 on 376 shows wavelengths. So if you've got 23 meter per second waves, that's basically 50 mile per hour in a storm. You've got big old long waves, 320 meters long. Average, something more like 15 meters per second, shorter wavelength, and if it's calm, you might have just a half a meter sized wave. 1 kilowatt per meter, that's where we were before with our single house per meter. 9 meters per second, maybe 20 miles per hour, and smaller wavelengths. That's kind of out on the open sea, like we're looking at here. Once we move inwards, though, it says as waves travel from deep water to shallow, their velocity reduces, and the resulting refraction generally causes the wave to approach at right angles to the shore. Well, so if you've studied light at all and sort of understand approximately how a prism works, with a light wave, it's kind of similar to waves on a beach. So I don't know if I can, how well I can, this figure actually shows it pretty well. So if let me try to draw it. Let's try to draw it here. So if this is the shore, and let's just say these are the waves coming in. This particular wave right here is going to hit first and slow down. right? And then this guy comes in behind it, and so what the authors are trying to show with this figure here is that the contours of the beach, the fact that it's getting shallower, actually bends the wave in, and that's why when you're on the beach, they tend to actually come straight into the beach, right? Just like you normally see. Here, this is more or less, they're not showing the riptide here, but if you've ever swum in the ocean, you've probably seen the fact that water is sort of coming in and converging in one spot, diverging in another, and then out here goes your riptide, right? It's got to go somewhere. Again, conservation of mass, but you can sort of see that in all of these cases, the wave is sort of bending, so it's more or less perpendicular to the shore wherever it happens to be. Okay, so when we go out and build our TAPCHAN or our oscillating deal on Flathead here in a couple of years, we'll take this into account. Okay, well that's 8.3. I'm going to take a break. I think we've got about 15 minutes left, and let's go from there.